Hello, my name is Xenia Trier, and I'm very pleased to be here today to talk to you about the sum versus sum of PFAS, how PFAS currently are regulated and how they could be. I work at the European Environment Agency for the past 4.5 years with cross-cutting issues relating to the risk governance of chemicals. Prior to that, I worked as an analytical chemist for about 20 years with compliance testing and enforcement testing, both in a private company and at the National Food Authority. And during this time, I did my PhD on PFAS, and I've been involved with the PFAS issue since about 2002. So in this talk, I would like to address 5 questions. First of all, what are the concerns for PFAS? Second, what are the pros and cons of regulating either single PFAS or the sum of total PFAS? Thirdly, how does this fit into the current risk governance frameworks? And then fourthly, I would like to address how, or give some examples of how PFAS have been regulated in Europe, both in legislations and also in the marketplace as voluntary measures. So examples of how the total PFAS and also the single PFAS have been regulated. And finally, since this is a student conference, I have given a few ideas to what further research questions could be addressed by you or other researchers. But first, what are the concerns? Well, there are multiple lines of evidence. First, as you probably know, it's more than 4,700 compounds that are PFAS. These are widely used across very many different use categories, about 200 are known. And because they are produced, manufactured, used, and disposed in very many different places, we will also have emissions from many different sources. And they're found everywhere in the environment. But what really makes PFAS specific is that they contain this carbon-fluorine bond, which is extremely stable, and that makes the compounds persistent. Either the PFAS themselves or their degradation products that contain these carbon-fluorine bonds will then not be able to degrade. And for that reason, they will accumulate in nature and inside our bodies. Either they will accumulate internally, typically the long-chain PFAS, or externally in the environment, which typically are the short-chain PFAS that are either volatile and go to the air, or mobile and very water-soluble compounds that accumulate in water. These mobile PFAS spread rapidly, and that makes them into long-range transboundary pollutants. And once they are out there, the very mobile compounds, they're very difficult to remove. So the pollution may be irreversible, so like impossible to remove, or very costly to remove. Also, the effects may be irreversible. So for instance, the child which is exposed to PFAS in the womb may develop a decreased immune system functions by these immunotoxic compounds, or have decreased fertility that they will be suffering from for the rest of their lives. So this together gives the PFAS the characteristic of planetary boundary threats, so chemicals that are persistent, that spread rapidly, and that are toxic. It also means that there are very many costs associated with PFAS in terms of the diseases they cause, the ecosystem services they degrade, such as the drinking water quality. And in terms of remediation, it could be falling and decreasing house prices or liability to companies. And in Europe, it has been estimated that about 52 to 84 billion euros is the cost of this pollution every year. And that is only for some of the single compounds. But let's have a look at how these chemicals then are risk managed. Well, PFAS are managed typically as single compounds across the world, as all the other chemicals which also are managed as single compounds. The advantage of that is that we have very precise and accurate chemical methods for them. We have standards for them so we can make them precise, but we only have them for about 20 compounds. I mean, you can do more, but typically it's maybe even just 2 globally, P4 and PFOS, and then the more advanced you have up to about 20 compounds. And this allows us to determine the occurrences of the PFAS, the hazards they have, identify their sources, exposure routes, environmental fate, and if there are vulnerable groups or areas that are particularly affected. It can give us some information about the mixture effects of chemicals that have the same endpoints. And this can together support the risk management actions. So address, specific sources or address, specific vulnerable groups. And the data feed in then to the risk assessment and management paradigms that are used to set limit values. The advantage that I think is the most prevalent for this approach of addressing the single chemicals is that they can be related to health effects, and that makes it easy and powerful to communicate why we have to take action or why we don't have to take action if there's no risk. However, the question is there really no risk? If we only have measured 20 out of 4,700, how are we sure that there's not an additional risk from the remaining compounds? One could then say, well, we don't have to measure everything because the 20 may correlate with the 4,700. However, for that assumption to be true, they would have to have the same source, or they would all have to degrade from the same type of compounds. But as we've seen, there's been a change from certain types of perfluoroalkyl acid precursors to other types of PFAS, such as the fluorinated ethers. And between the two of them, the alkyl acids and the ethers, there's not much of a correlation. So really, these are not very relevant markers of exposure, but or at least we don't know yet because we don't have the full overview. This also gives then a bias to what is really the total risk, and we have a risk of having false negatives. There's also a bias in which chemicals that are tested, because it is always easier to include another compound that have the same similar characteristics as those you already are analyzing in your method. So to give an example, if I have a method for the perfluoroalkyl acids, they are anionic, and then it's much easier to include another anionic PFAS into my method. And on the contrary, if I have a non-ionic compound such as a fluorotelm or alcohol, it would require to use a different instrumentation, and I would have to set up a new method and validate it, etc. And I'm less likely to do that. So there's also a bias in which we test. This together means that, we have to have pretty advanced and costly instrumentation and skilled personnel to include all these different compounds. And once we have these results, they can be difficult to communicate to the non-experts because we have all these different compounds. So to give an example of, are we really capturing the majority of the PFAS with looking at these 20 different compounds, or are we overlooking a lot of unidentified PFAS? I would like to give you an example here from a Nordic study of PFAS in the environment. And what they did here was that they took samples from fish, marine mammals, bird eggs, and terrestrial mammals. And they investigated with methods for both total furring and saw what was the result there. And then they tried to identify and quantify which fraction of that signal could be explained by the specific PFAS. And this is what you see in the figures here below. I don't want you to read everything, but the main point is that you see some bars here, and the part of the bar which is white illustrates the fraction that has been explained by the specific PFAS. And the fraction of the bar which is black shows which fraction that is unexplained, so unknown PFAS, that we have not included into our methods. And I should say that they actually included many more than 20, so they included all of those PFAS for which you have standards. So there is a big fraction which is unidentified, at least 50% in most cases, sometimes more. And this really is what calls for the need for having a method for the sum of total PFAS. As I've already said, the advantages is that they can detect both known and unknown PFAS, and this provides an option to have an early warning screening. They can also help to prioritize whether you need to go into further investigation, or you can kind of drop it and say it's good enough, no, there's no concern here. Methods that are cheap and fast are available, and this can increase sampling frequency. And these simpler results can be easier to communicate to non-experts. However, there are also screening methods that are very advanced and require costly instrumentation, but they can give you information on the chemical structures, such as the non-targeted analysis, fluorine NMR, and to some extent also the total oxidizable precursor. On the downside is that these methods are semi-quantitative by nature. They cannot really be related to the health effects, because when you have measured just the fluorine constituent in a compound, it doesn't really tell you what the structure is, and therefore you don't know what the health risks are. There's also a risk of getting false positives, because if you've only measured, let's say, inorganic fluoride, then there might be inorganic fluoride not coming from organofluorine, but just being present in the water as inorganic fluoride. And that is not really part of the risk assessment you want to do. But there are ways around this where now you have better sample preparation techniques where you can avoid these false positives. However, every time you add another step to it, it becomes a little bit more complicated and costly and takes longer time. Another thing is that the current methods are not fully developed yet. I would say they could still be improved in terms of their method performance, and they could be standardized, and more people could pick them up and use them. So testing capacity could increase. And just one last thing about this, the health effects, that they don't really inform you about the health effects. One way around that could be that you make a boundary analysis. So you say, well, in the worst case scenario, if all of the signal came from one of the most toxic compounds like PFOA, what would the health risk be then? And then you can take, let's say, a lower bound analysis that, well, in the best case scenario, if everything comes from one of the PFAS that is the least toxic, what would the health effect be? And that can help you to guide, the risk is somewhere in between these two values. So there are still options of how you can apply this in a more health-based setting. So in conclusion, which ones of the methods are the best to use? Is it the sum of single compounds or the sum of total PFAS? And I would say both. And I would now like to show you how these two different complementary methods can fit into an existing risk governance framework. And I've taken an example here from the International Risk Governance Panel. And as you can see, it consists of different elements, where the first part explores the knowledge and tries to develop an understanding of the problem. And in the second part, there's a decision phase of how you want to manage that risk. So in the pre-assessment stage, this is where you can use the sum of total PFAS. But the first step would be to understand what is the aim of the regulation or the investigation, which level of precaution do you want, what information do you have on past and current uses, etc. And the screening methods here can then serve as an early warning tool to assess the level of contamination, and then help you to decide whether you need to go further into an investigation and do a risk assessment. And in this next step of the risk assessment, this is where you have the sum of single PFAS. Because here first you could do the monitoring, find out which PFAS are there and in which levels. And then once you know this, you then have the hazard characterization possibility. And together then the exposure assessments and hazard characterization can inform the risk assessment. In the next step in the appraisal phase, you go into a concern assessment. And what you have just done right now is you did a risk assessment that gave you some information about the health concerns. But as we all know, there are other concerns. I mean, it's also like, how worried are people? What are the risk perceptions? Are they, and these risk perceptions may be different from citizens, communities, businesses, institutions, and you need to know, like, how worried are people or not. There may also be social concerns, such as are there certain vulnerable groups who are less resilient in dealing with the impacts of pollution, for instance, if their health is affected. And that also brings it down to, like, what are the socioeconomic impacts of it, both of inaction if you do nothing, or action, and there may be different types of impacts there. So this brings us then to the next phase of the decision making. And here you go into the characterization and evaluation, and you do a risk evaluation. And this is different in nature of the previous steps, because here you come more into a value judgment. And here you have to decide more from an ethical point of view. Are you willing to fail to protect the public consumer environment against these unmonitored PFAS? Are you willing to accept the responsibility in that case, both if you take action or also if you don't act? What are the elements of fairness and justice of those who are benefiting from causing the pollution, from not putting filters on their smokestacks or emitting into the wastewater, versus those who are suffering from the pollution? And are you willing to lose trust if you do something or you don't do something? And so in the decision-making step in the management, you then have to bring all these elements together and figure out what is the best way to address this. Do you manage either some of the single PFAS, set limit values for them? Do you address the sum of total PFAS, or do you do a combination? What is practically and economically feasible? And if you figure out that none of this is what you would like, are there other options of how to address it? And that brings us to the next, please, which is the management and the implementation. And this step, I think, is often overlooked, but it's really important, because we may have a lot of regulations, but the best regulation is the one which is implemented. And many good regulations are not implemented well and are not tested or enforced well enough. And part of the reason for that may be that the control methods are too complicated or too expensive, or not the personnel is not trained in it. So part of the assessment here is to ensure that the control methods are implemented, that they have the sufficient quality assurance and robustness, because for these methods you need to know is a result, is that compliant or non-compliant with the limit value. You need to have this yes, no answer. And so you cannot have maybe, because this makes everything very complicated in risk communication, for instance. And you also should have some decision charts of which actions should be taken by whom in case of non-compliance. You need to train the personnel of how to do all these processes and understand it and communicate it to the relevant partners. And then you have to follow up on the implementation, which means you have to, after a while, check, did it work or didn't it work? So in summary, we have regulations of some PFAS versus the sum of total PFAS, but they complement each other. Limit values can be established for both, and they both have uncertainties associated with them, but they're different in nature. Some has more of a bias, some has more of a precision issue. The scientific assessments feed into the concern evaluation, but it's one of several concerns, and they need to be taken into account. And depending on the context, you may choose to use either the sum of total PFAS or sum of single PFAS, and also very much depending on who's going to use the data. Is it experts or non-experts? And this takes me to the examples. So examples of where these methods have been applied is, for instance, in Denmark. Since 2015, there's been a limit value for PFAS in groundwater for 12 single PFAS, also in soil for 12 single PFAS with limits values set. Similarly, for the class of PFAS in food, paper, and board packaging, where since 2020 there's a limit value for all of these compounds. It was the first actually in the world that required that there shouldn't be any PFAS in the paper and board. And prior to this, there had actually been limit values for the single compounds, but it turned out that the development in the technologies was faster than we could update the methods, so they kept changing the PFAS, and that meant that in the end we could still see that there was PFAS in it, but we couldn't measure it with the specific targeted methods by LCMS. And that was really what pushed us to develop methods for the total PFAS. But as you can see here, the indicator value is pretty high, and that is because it's not a health-based value. The value is set to prevent manufacturers from intentionally adding PFAS into the paper and board, but it is set at a level which is still high enough that recycled paper and board which may contain small amounts of PFAS can still be used. And in the marketplace, similar approaches have been taken. So at the beginning, typically it was single PFAS such as PFOA that was mentioned, and that was avoided and tested. But nowadays there's more of a trend to measure the total PFAS, and it's very many responsible front-running companies that have taken this up voluntarily. In EU, we have also had updates of our drinking water directive, which is now a combination of 20 single PFAS, as well as a sum of total PFAS. And for this sum of total PFAS, there's actually a transitioning period until the method is considered fully evaluated and standardized. And after it has been that, then the countries can choose which one of the methods they want to apply in their countries. And EFSA came out also with an opinion recently here in September for a group of 4 PFAS, so that is like sum of single PFAS, and with a very low level of 4.5 nanograms per kilo body weight per week. And that should protect the children of year 0 to 1, so infants that are breastfed, and the levels are set for the PFAS levels in the mothers to ensure this. And the concern were for the reduced immune systems that these PFAS can cause for children exposed to it. The industrial level, we have the REACH regulation in the EU, and here we have different types of regulations. One is the restrictions, which apply to all products that are made or imported into the EU. And here it's mostly the sum of PFAS of larger groups of chemicals, so PFOS and its derivatives, or PFOA and its precursors, and many others, including PFAS in firefighting foams recently. But there's another type of regulation which pertains to chemicals that have been classified as substances of very high concern. And here they should be substituted, but uses may still be authorized. And there's a tendency to have more of a single PFAS. And as you can see here, a very interesting thing is that some of the short-chain PFAS alternatives are mentioned, and they have been included despite that normally this SVHCs are based on chemicals that have properties that are persistent, bioaccumulative, and toxic. But it also says or chemicals with equivalent level of concern. And here recently, the mobility of PFAS was included. So at the EU level, we are now awaiting very shortly to see the EU Chemical Strategy for Sustainability, which addresses also PFAS. And here, this class of PFAS will be addressed across legislations and will be required to be phased out for non-essential uses. There's a requirement to update the legislations accordingly, but also to increase the monitoring and reporting of both single PFAS and the sum of PFAS. And the follow-up to this will be an action plan of how to implement these requirements. So this brings me to the last part, which is which questions remain? Well, many. And if you're studying PFAS, you can do it for a long time, I assure you, because there's so many different compounds. But in relation to this sum versus the total sum, we have a need to set and understand which limit values are appropriate for the total sum of PFAS that are sufficiently protective to be relevant, but also not so low that the majority of the samples are non-compliant. And to understand this, we also need to understand which other PFAS have limit values. For instance, fluorinated pharmaceuticals and fluorinated pesticides may have limit values. And we need to understand, do they conflict and create false positives? And then we need to also understand and better develop the screening methods for more matrices. Ensure that the sensitivity is low enough to be relevant, and also that we have methods for many different media. And once this is in place, it would be very nice to see more monitoring studies of specific and total PFAS in more matrices, including products that are going to waste. This is a big wish from the Commission. They lack that type of information for the next steps. But I think also it would be interesting to see studies in human fatty tissues, sediments, and soil. And finally, I think to sum it up, all of these PFAS tend to be toxic, but we still know very little about what the toxicity is. What are the modes of action? What is causing the toxicity? And this is very important to inform how we can group the PFAS, the single PFAS, but all into mixture assessments, but also to guide the future substitution to safer chemicals, so that when we substitute to something, that we don't have chemicals that also cause effects or similar effects, even if they're not fluorinated. And with that, I would like to say thanks for listening. You're welcome to contact me if you have questions. And I would say it's fascinating to work with chemicals because you're always just looking at the top of the iceberg, and the more you dig into it, the deeper you know it goes, and the more you know you don't know, and all the uncertainties. But thank you for listening today, and have a good day.